So fundamentals of Python, first programs. Describe the basic features of an algorithm. Explain how hardware and software collaborate. Maybe not. Give a brief history of computing. Maybe not. Compose and run a simple Python program. Alrighty, so this is one of those chapters. The first chapter in every programming class is always a history of programming. And while it's interesting to read, I'm not necessarily going to walk through it very carefully. Okay, so.
Professor?
Yes, sir.
All I can see is your
You
icon.
can't see nothing. All righty, thank you.
I cannot see the screen. No problem.
Let's catch that early. Thank you very much. All righty, what's the deal? All righty, thank you. Okay. Because weirdly enough, I can see my own screen. Just kidding. Okay, so what is an algorithm? It's a recipe. You have a recipe for making cake. You have an algorithm for solving some other kind of problem as well as making a cake. So for example, the steps for subtracting two numbers. You could write the numbers with the large number above the smaller one, the digits column aligned, and then you could start with the rightmost column of digits and work your way to the various columns. Write down a difference between the digits. Okay, anyways. And so in that case, when we're doing that, handwritten subtraction on a piece of paper, the computing agent is the human being. And so the sequence of steps that we follow in order to do that is called an algorithm. So the features of an algorithm. It will contain a finite number of instructions, and each individual instruction is well defined. That action described by the instruction can be performed effectively by a computing agent, even if that computing agent's a person just, pretending. Describes a process that eventually halts after arriving at a solution to a problem and solves a general class of problems. So computers can be designed to run a small set of algorithms for performing specialized tasks. I don't get that statement. So information processing information is commonly referred to as data or data. Guess we're supposed to call it data, but Star Trek Next Generation convinced me that we're supposed to call everything data. In carrying out the instructions of an algorithm, computing agent manipulates information. You start with your input, you transform input according to well-defined rules, and you produce output. So even a video game like Pac-Man starts like that. What is your input? Well, the input is it's waiting for you to press this play button. And once you press the play button, it responds to the input of the position of the joystick. And then based on that joystick, it transforms information inside itself, keeping track of where Pac-Man and the ghosts are on the screen, and then continually producing output and getting new input in order to repeat. So the algorithms that describe information processing can also be represented as information. That's a little abstract. That's kind of mind-blowing there. But yeah, okay, since algorithms are information, then they can be represented as information. I am not sure what I'm going to do with that statement either. So computer scientists have discovered how to represent many other things, not just text and numbers, but images, music, human speech, and video. So modern software, computer system consists of hardware and software. Hardware is what you touch, and software is what you can't. So the physical devices is the hardware. The software are the algorithms, which are programs written in particular programming languages. So your basic hardware components, you know what? We're just going to skip a little bit through this. All right, so programs stored in computer memory must be represented in binary digits or machine code. I really need to do a video I give a lecture called, about chip, the CPU, and how it is run. And people who've taken my fundamentals class have already seen it, but it requires me writing on the whiteboard for people to enjoy it. So I need to come up with a way of how I'm going to do that. But all a CPU is it's a device that responds to numeric commands by doing things to other numbers, right? You can give it a numeric command which says read from this memory location. And then you can give it another command that says write to this memory location. And then another one that says add these two numbers together, right? And then another numeric code that means compare these two numbers. And if one is less than the other, then jump to a specific location, right? And so the machine language is a series of numbers, but we don't want to program in a series of numbers. And that's amazingly hard. So very, very quickly in the development of programming, people came up with the idea of programming languages that where you did not have to write in machine language, you did not have to write out a series of numbers. Instead, you could write using a programming language. And so the most primitive programming language would be something that looked like this. I'm just going to grab one at random. All right. So if I'm not mistaken, these things here are just comments or labels. And then these are the opcodes, the things that tell the chip what to do, but they have been given names rather than just numbers, to make them comprehensible to us. So move some data, move some more data here, move some data here, set this bit, set this bit. Nop means no operation. It basically you just mean don't do anything for a minute, okay? But it's given a label so that something can jump to the loop. And then so this says S jump back to loop. And so it just goes back to that location over and over and runs infinitely. Now there has to be some way to get out of this. And they're talking about some kind of interrupt, and there must be some way of getting out of it. And I don't know how. But anyways, so this is obviously not very human readable, right? It's not much better than if we just had to try to, write with pure machine language, writing down numbers, right? But at least we have these little mnemonics, move and jump and clear and complement, CPL. Somebody did a good job of commenting, right? They put all these comments down here explaining, what it did. So the moon language, the moonlanders, NASA's moonlanders were also programmed in assembler. It's fine. Oh, come on. She was critical to the success of the mission. Where's my... So yeah, you can go to GitHub, which is a repository for code, and you can download the programs that landed, things on the moon. And yes, it is also a machine language, written in assembly. Just wanted a cute example of it. I like that picture of her. Well, here's what the input output looked like, right? You had some keys that you could press. And then buttons would light up as a result. And that interfaced with the computer. Oh, anyways, you will notice that they added a comment for just about every single line of code, because if you were looking at this stuff and you didn't have the comments here, it'd be very difficult. I mean, you know, if you programmed in this every day, you'd know exactly what the commands meant, but still, in order to note, to annotate the structure of the program, the comments are incredibly important, especially when making a mistake could cause your rocket to blow up, right? Kill some astronauts. So hello there. For generalized return to other ranks, subroutine, do check return, yes, check for auto throttle mode. Anyways, I've always kind of thought it'd be interesting to go through this, and then I never do. But it is certainly interesting that it is out there. And you can imagine the rigor and care and attention to detail that would be needed to do something like this. But we would rather write in a more English-like programming language. Well, just because we speak English, right? I mean, if we spoke Russian, we might want one that looked like Russian, but oddly, most of the vast majority of languages on the planet are written with an English-like syntax, just due to history of who invented what and then what got popular. So we don't, a program to add two numbers. So up here, we declare two variables, num1 and num2, and then maybe a third variable called result. And num1 has got a 9 in it, and num1 has got a 7 in it. And so we move something into one location, we move something into the other location, and then we call the add function, and then we move the result, and then we call it 21H, which probably is some kind of print command to display the result. I don't know, strictly speaking, but I would much rather just be able to do something like this. A is equal to 9, or, you know, num1 is equal to 9, num2 is equal to 7, and then do print num1 plus num2, right? There. That makes me a lot happier than that. We can get a lot more done with our high-level programming languages. High-level meaning that they are more abstract, and that, you know, a single word can represent a whole number of steps, and not just, you know, microscopic atomic steps one by one. So the most important example of system software is the computer's operating system. Am I annotating it, or somebody else annotating it? Where'd this come from? Just you and me, and I doubt you're annotating it. What's the deal there? Huh. David, do you see those things on your screen? Green lines?
Yes, I'm sorry. I've made some. Let me trying to.
Ah, okay, good. So there's a reason for it. It's not it's not a complete. That's good to know. All right. I'll stop mine.
Get him. Okay.
Yeah.
I'm terribly sorry.
Hey, no problem.
I'm cleaning at work while I'm watching this.
Yeah.
I'm muting.
So the operating system will control things like the file system, where we store our data to and read data from, and the user interface. We're going to be, by and large, writing terminal programs, command line interfaces, which are just programs that pop up text and then display text as a result. But we can also write graphical programs as well. And it'd be cool to do a touchscreen interface, but I don't know how to do that with Python. And then so applications, you know, anything that you want the computer to do, web browser, word processor, spreadsheets, database managers, etc. So high-level programming languages have been developed for expressing algorithms. The reason that they were created is to resemble a written language, most of them English, and allow the author to express algorithms in a form that people can understand. And so programmers usually start by writing high-level statements in a text editor. And then a program runs called a translator that converts that text into executable code. And then a translator checks for syntax errors. And we do the same thing. It just doesn't really feel like we're doing two different steps because this is our text editor, right? I can create a file. I stepped it out again a little bit more slowly. I went to idle and I chose new file. This being Lecture B, I'm going to save as Lecture B. And I'm going to add a comment up to the top. All right, and then I could write my program, right? Maybe we could ask the user for these numbers. We might want to ask for these numbers, but let's make it a little bit more basic than that. Let's write a program that just asks for our name and then displays a hello message back to us. And so to do that, I'm going to use the input function. I'm going to create a variable called name, and name is going to contain the results of the input. Now we need to tell them what to type. Otherwise, they don't know what to give us. They'll just get a blank screen with a question mark, right? And they won't know what to type. And so then once we get their name, we can convert it. I mean, we can display it on screen. Print, hello, end quote. So hello, parentheses, quote. I was not reading this as I wrote it off. Print, parentheses, quote. Hello, comma, end quote. Comma, name. Now this is looking really stupid and I'm not liking that where I'm taking it. And I'll show you why. I'm going to finish that, but then I'm going to revise it. And I'm going to make it look, starting off on day one by showing stuff that's not even in the book. How's that? Or anyway, so if I type in that my name is Fred, and it says, hello, Fred, and I put that space there, and I don't like that space. There's other things I could do. I could replace these commas with plus signs. That'll make it look a little bit better, right? What is your name? Fred. Hello, Fred. Now, something that was recently added to the Python language a few years ago is a modified form of print statement that I'm actually going to use early and use often because I think that it makes the code easier to read. You may not agree, in which case you are free to not do it in this style, but it's called a formatted print. And the way it works is you say hello, comma, and then inside curly braces, you put the name of the variable you want to print out, like that. Right, so those do the same thing. If this one makes more sense to you, you can stick with it, but I am going to be giving lots of examples of this one. Now, if you're going to print out numbers, you can't use the plus sign to print out the number, unfortunately, because plus and numbers means addition, right? And here's not doing adding. The plus sign when talking about strings, which is what text is called concatenation. And so concatenation works great when there's strings, but what if we had a number, like our age? Well, if we said that our age is 32, and we wanted to print, come back, print your age might be, end quote, plus age, right? But that's not going to work. That's probably going to be a syntax error. Of course, it doesn't tell me that until I actually start running it. And then boom, it blows up. Line 9. Oh, line 9 had a problem. Okay. I'm going to go over here and enable line numbers so that I can figure out where line 9 is. So I'm going to go to Options, Show Line Numbers. And sure enough, that's the problem. The problem is that you cannot add words to a number. You can add numbers to numbers and you can add words to words, but so what are we going to do about it? Well, there's the easy way to fix it, and then there's a slightly less easy way to fix it, but both of them work just fine. One is that we could take this number and we could convert it to a string so that it was text, just like all the others. Now that's not going to be a syntax error. That's one way. But it'd probably be clearer, easier if I just used a comma instead. And if you separate things by commas in a print statement, you don't have to convert them to strings. I'm going to get real tired of typing infrared here. That's the problem when you write a program that asks for input and then you run it over and over and over. Okay, so I don't like that output. There's an extra space there where I didn't want it to be, but that's easy to fix. So one thing to note is that when you're using the plus sign, it doesn't put spaces automatically, but when you do commas to separate your parameters of a print statement, it does. And if I was going to use this formatted print style, print your age might be, and then I would put in curly braces, end quote, in parentheses, and what data am I going to print between the curly braces? The name of that variable is age. Well, that was a mistake. What did I do wrong? If you're doing a formatted print, you got to put that F there. All righty, so 3 different ways. You get to pick which way makes sense to you. Probably that way. That'd be my guess, but maybe I'll convince you that that's a pretty cool way of doing it too, right? Why am I saying that that would be a pretty cool way to do that as well? What if we had several pieces of data that we wanted to print on one line? Like a first name and a last name and a middle initial or something like that. Or a city and a state and a zip code. So the city might be Del City. The state might be Oklahoma. And the zip might be, oh, check that out. If you start to type something and it turns purple, that means that it's a function or a predefined keyword. And we shouldn't use it. And so I don't even know what that does. That's fascinating. All right, so how about the whole word zip code is equal to 73130. That's not Del City zip code. That's a Midwest City zip code. Since I don't know Del City, I'll fix that. All right, so Midwest City. And so now we're going to print a message that says, you might live in Midwest City, okay, 73130. Using the F format, I could make it look like this. Print, parentheses, F, quote. I'm going to go ahead and finish the whole thing first here. So end quote in parentheses. You might live in city, state, at zip code zip code, right? And when it runs, it's going to fill in. That placeholder gets filled in with OK. That placeholder gets filled in with, whatever, right? City is going to be that. Let me add some spaces to make that a little bit clearer. I pointed the wrong one. So the city is going to be Midwest City when it prints out. The state's going to be OK. And then the zip code is going to be 73130. And so we're going to see the message, you might live in that, right? Okay, now we shouldn't have assigned an age. We should have asked for the age, right? So this really should have been an input statement here in order to get the age. So let's change this to an input statement. We're going to ask them their age. So I could do that. But that's not really good enough. I need to tell them what to type, and I could add a print statement to tell them what to type, or I can just indicate what I want them to see right here. Now, by the way, this is going to crash because I did not convert it to a numeric format. When you type stuff in from the keyboard, it's just text. It's called a string. And the computer doesn't know what kind of string it is. It could be all Z's. It could be a perfectly good number. But when we try to do math with a string, it's like the plus sign failed because you can't do math on a string. It has to be converted to a number. Oh, well, it didn't crash. But I don't get what it did. Where did it come up with 2? Yeah, we didn't never actually do any math with it, and that's why it didn't crash, right? If we were going to add 1 to it to say what we might be next year. Well, how odd. I'm going to add a line here that says age equals age plus 1. And then I'm going to say next year, your age might be, and so now I'm going to just copy and paste that right. So I don't have to type it 3 times in a row. Well, okay, there I got my crash, which is what I was expecting. I really can't explain why it ignored my 3 there. It totally blows my mind. But I got an error in line number 10 saying that you can only concatenate a string, not an int to a string. In other words, I'm trying to add 2 things together and they're not of the same type. Age is a string because it was typed in from the keyboard. Even though I typed in a number, the computer doesn't know that. I have to convert it to a number. And so I could do that with a separate line of code like this. And now we're good to go. Well, good. That time it took both numbers that I typed in, not just one. Okay, so this is an example of getting numeric input. This is an example of getting string input. The input function can optionally accept arguments that describe what you should type, right? To indicate what is displayed. Here we did not, and here we did. You know, I could put like a little quote greater than quote, and then that they would know that they were supposed to type their name there, right? I could have done the same thing here. I could have typed in a couple of spaces and then a greater than, and then they would have that little cursor symbol telling them where to type. Like that. And that's kind of my preferred style. I like having the cursor telling them where to type. Notice that when you ask for the input, if you separate it into a print followed by an input, it comes in this format. The print displays that, and then the input happens on the next line. If you have it all on one line like this, then an output is displayed on one line, right? And then the input happens on the same line. So just kind of however you like to do it. So anyways, that kind of ran far off of field. What are we doing? We're typing in our statements in a text editor. Idle is a text editor, just like Notepad is, right? Or, you know, whatever your favorite text editor is on whatever kind of programming, on whatever computer you use, whatever operating system you like. When we want to run it, it has to be saved to disk. That's why it's always asking me to save to disk. And then it does something called compiling. And what compiling does is it changes our English-like text into the series of opcodes, into the series of machine languages necessary to interact with the computer. And if there's a syntax error, or if there's something blatantly wrong, like if I forget to close my parentheses there, then the compilation will fail. It says invalid syntax. And real helpfully, it doesn't even tell me where. Oh, at least it highlighted the cursive there. Now, one thing about syntax errors is you may look at this for a long time and go, but I spelled that word perfectly good. There's nothing with that line. Well, when it tells you that there's a syntax error there and you just flat out can't find it, go to the line above it. It's probably in the line above it. And in this case, that is the case. I was missing that. So far, we've seen the three things that they've talked about. We've seen this getting of input. We've seen the manipulation of data. And then we've seen our output. So the text editor, the translator runs, and if it fails, it kicks out syntax errors, messages. I would usually call that the compiler, but whatever. And then if it works, then what? The result of that compilation step is sent to the runtime system. Python is a runtime system. You may have played video game emulators, right? Where you want to play Nintendo games on your PC, or you want to play, you know, old, you know, arcade games like Pac-Man and Space Invaders and stuff like that. An emulator allows opcodes written for one language, one platform, one system to run on another system. And so that's how you're able to play Pac-Man on your PC or whatever. It just takes that binary data, which is opcodes, you know, written for a very specific set of hardware, and then it provides the emulation environment that takes that binary code and runs it as though it were that hardware. So then you could be playing, you know, Super Mario Brothers on your PC. Well, Python does that step of emulation based on what is fed to it from the translator. And the reason it does that is so that Python will be compatible on a large variety of platforms. If you have a language like C++, when you compile it, it produces an executable file. It produces object code. It produces machine language that is tailored for the very specific language that you ran the compiler on. And you get a program that can only run on that computer. But that's not what we want. So instead, what Python does is it creates an intermediate form of language. And then they have a runtime system which takes that intermediate system and interacts with the operating system. And so the same language can be written to run on many different platforms. I don't think I gave a good enough example of that. I may have to bone up on that a little bit. major, not so brief history of computing systems. I'll let you read that. Early computers, the abacus, and the Pascal calculator. This is, in fact, a calculator. You want to do some math? Well, you set the dials to indicate what numbers you were doing. And then you would set the switches to do some kind of operation. And then you would turn a crank and it would do the math for you. Looks incredibly tedious, doesn't it? Well, yeah, but it would be better than doing it all longhand, you know. And then here's Babbage's analytical engine. No, that's a printing press. That's a Jacquard loom. And the reason that they're giving this as an example of an early computing device is that it was programmed by punch cards. And then the same idea was used by a guy named Charles Babbage to make a mechanical computer in the 1800s. Now, if you're used to the idea of, or maybe you've read something called steampunk, right? And steampunk is where what if technology had gotten really sophisticated in the 1800s, but not with digital, electronics. Instead, it was all, steam powered and stuff like that. And that's effectively what this was, is a computer that was run on mechanical power, and it was programmed by using punch cards, and the data was stored. And I don't know how the data was stored, via giant wheels or what, but it was a fully programmable computer. Unfortunately, it never ran because he ran out of funding and the machine tolerances for grinding your brass wheels at just exactly the right, precision in order to do this. It never really fully came together. But he and his partner, she even created a programming language for it. She was the programmer for it. He was effectively the hardware designer for it, and it would have worked. And nowadays, people have made them because machine tolerances and milling precision is much better than it was back then. And so, like, you can probably find one of these, at the IBM headquarters and in museums and this and that and the other. So that's what we're seeing. So Charles Babbage conceived the analytical engine. Well, he conceived it and even built it. He just did not get to finish building it. Herman Hollerith developed a machine that automated data processing for the U.S. Census. He went on to form a company called International Business Machines. George Boole developed Boolean logic. Boolean logic is logic that's all about ones and zeros, or trues and false, actually. Trues and false. Boolean math is a math in which there's only two possible values, 0 and 1, or false and true. And then you can do things with that. Alan Turing explored the theoretical, okay, well, these are really vaguely stated, and I am just going to skip past this because if I started talking about this, I could go for hours and hours and hours because it's fun. So the first assembly languages did have operations like add and output. Programmers entered codes for the operations at a key punch machine. And so your programs were written on cards, punch cards. And then those punch cards were fed into the computer, and an assembler would translate those programs in memory to machine code, and the compiler would translate the programs to machine code. What's the difference? An assembler is a compiler. It's just a compiler for a very specific form of machine language. Hope you're reading fast. No, I'm kidding. You can go back and read this, and you can read the textbook, and there really is a lot of interesting stuff here. And here's our man, the inventor of Python. Guido von Rossum invented the Python programming language. It's an incredibly popular language. It's like one of the top 3 programming languages listed in, in job hunting. I believe that to be true. High-level general-purpose programming language for solving problems on modern computing systems. So, things to know about Python. Python is an interpreted language. What's the difference between an interpreted language and the other kind, which is a compiled language? Well, with a compiled language, you write a file, you write a program, you press a button, and then it saves the result into an executable. It compiles it into an executable. And then you can mail that executable to somebody else, and then they can run it, right? They have an app, they have a program that they can run. But an interpreted language, it doesn't get compiled into a file. Instead, the interpreter reads it one line at a time, processing it, and using the runtime system in order to run it right on the spot, rather than to create an executable file that you run later. So it's immediately interactive. It doesn't save it to a file that you then have to double click and run. Instead, it's immediately interactive, and each line is processed line by line. So simple Python expressions and statements can be run in the shell. When I launch idle, I get that shell. Like if I quit it and relaunched it. I guess I didn't close it completely, so it's not gonna, Anyways, you know what I mean. When as soon as I run Python, I get this shell. This is the interpreter. I can enter commands into it if I wanted to. A is equal to 3, right? And then sure enough, oh, all right. It was still in the middle of running my program. All right, A is equal to 3, B is equal to 4, C is equal to A plus B. Print C, right? And so I found out that 3 plus 4 is 7. It's interpreting it line by line. One line at a time is being processed in order to do this. Now, what if I made a mistake and A was really supposed to be 7, right? And it's 3. Well, I'm going to go back and change that. No, I can't. That's the problem with trying to do your programming in the shell. Instead, you want to save all these statements and write a program that does it. And so that's why we do file, new file, and create a file to where we can enter all of our code and then save it and then tell it to run it line by line. And so it was being typed into the shell right there. Get my lecture back. So the easiest way to open a Python shell is to launch idle. I think we can figure out how to quit. Control D, huh? If I type in Control D, it's going to quit idle. What's up? No, I don't know what it's doing, but it's not quitting it. I never noticed that statement before. What if when you're currently running it, you type in Control D? I don't know what they're talking about. We know how to quit a program. We just click the close box, or we come and choose the quit menu, right? And so that's called the Python shell. And it's useful because you can experiment with short expressions or statements, and you can consult the documentation. So when we launch it, it pops up and it tells us, it's licensed. This author must have been using a Mac. And so programs usually accept inputs from a source and then process them and then output the results to a destination. In a terminal-based interactive system, these are the keyboard and the terminal display. And that's kind of what this looks like, even though these are far more sophisticated than the old-fashioned terminals used in the 60s and the 70s, where you just had a black screen, right? And a and a typewriter hooked up to it. You can type keys on it and see them pop up one by one on the screen. So in Python, the input are Python expressions or statements, and outputs are results that are displayed in the shell. Programmers can force output of a value by using the print function. So if we went to the shell and we typed print hi there, then it would print hi there. Except the creator of these slides did not take great care to make sure that everything was perfect. And one of the problems they did is that they let PowerPoint put in these matching quotes. Matching quotes don't work in a programming language. They look nice and pretty. But if I went out here and I tried to run that, you can see that we have the open quote and the closed quotes. And when I try to execute it, invalid character in identifier. So it just did not know what it was. So what it needed to look like, and if I had all the time in the world, I would modify all the PowerPoints appropriately. So that it did not use the matching quotes. And I know that the matching quotes is something that you can enable and disable when you're typing stuff into PowerPoint, and the guy who created these did not disable them. So I'm just warning you that this code examples here, quite often you'll not be able to copy and paste them, and that's too bad. Another thing that they forgot to do is to indent code, which is absolutely insane. There are places in here where the code needed to be indented and it is not. And it's just flat out insane because it won't run if it's not indented properly. As we go on, we will find out that Python insists that code be indented in certain places, and if it's not, it won't run. We may as well give an example of that. I'm going to go back to my lecture. And down here, after I say you might live in city, state, whatever, I'm then going to check. I'm going to check to see if their name is Fred. If name equals quote Fred, end quote, colon, then we're going to print a message. Hi, Fred. Where's Barney? That's a Flintstones reference. Fans of classic 60s cartoons. Okay, so I have a colon here because this is a logical construct. The colon means that the next line has to be indented. And everything that's indented after this colon will only be done if this is true. If the name that they typed in is equal to Fred. I can add an else down here. Print, sorry, I was looking for Fred. Right, so if name is equal to Fred, print hi, where's Barney? Else, print sorry, I was looking for Fred. The indentation tells it that this code is subordinate to this if clause, that it is only performed if this is true. And this is only performed if the if wasn't true. And this could be one line of code or it could be 100 lines of code, right? As long as it was all indented, it would be run if this statement was true. If you don't have it indented correctly, though, it'll crash. Some languages don't insist upon indentation. I never say that. Python does. Python absolutely does insist that things be indented perfectly, and it can get very annoying sometimes. But you do have to have the indentations, and if you don't, the code won't run. So there are code examples, and as we run across them, I should make changes to the PowerPoint and then upload them back, and so I'll try to remember to do that. I'm not going to bother fixing the double quotes, but for longer chunks of code that need indentation, hopefully I'll remember to change it and re-upload the modified PowerPoint. So the following example receives an input string from the user and saves it for further processing. Name is equal to input, parentheses, quote, enter your name, colon. And so then when that is executed, It displays the name. Enter your name. We are allowed to type in something, and that result is stored in a variable called name. So name equals input parentheses quote. What is your name? All right, so my name is Fred. It's not. I don't know why I'm stuck on Fred today. All right, and so then if I type in name, Fred. Now normally I would type in print name, right? Because that's what the program would need in order to display the message. But in the interactive shell, you can check the values of variables just by typing that variable name. Like if I do x is equal to 3, and then later on I want to find out what x is, I can just hit x like that. But in a program, I would do print x. Going to do the same thing. I could try to find out what kind of information that name is by doing type. Type, parentheses, name, in parentheses, describes what the data is. It's a string. A string is a series of characters that was typed in from the keyboard. What about that number there? What type is it? Type, parentheses, x. It's an int, standing for integer, which is a whole number. Broadly speaking, there's two forms of numeric data that we use in these programming languages: floating point data and integer data. Integer data is whole numbers. Floating point are numbers with decimal points in it. So if I do x is equal to 3.1, and then I say type x, it's not an int anymore because an int is a whole number. It's a floating point number. And you may wonder why it matters, but to the computer, floating point math and integer math are handled by entirely separate circuitry. And so they have to be stored representationally different. Even if they don't have the same, even if I say this, A is equal to 3 and B is equal to 3.0, the ones and zeros in computer memory that represent that in that are completely different. Completely different series of ones and zeros are required to store these two things, because this one has to support, well, I'm not going to even get into why. They're just completely different representations in memory. But we don't normally care about that, right? We just think it's a number and we want to be able to use it. And so the programming languages make it pretty easy for us to, deal with them interchangeably. I could do something like C is equal to A plus B. And so it'll add those two numbers together. And so when I print it out, it'll give us a nice answer. Now behind the scenes, there was some stuff having to go on. Since these are not of the same type, they're stored in completely different formats, what Python had to do is to convert them both to the same format, because math can only be done on this objects of the same type. Just like we could not add a number to a string. It was complaining about that being a syntax error. Well, if you add an int to a float, that would be a syntax error, except for, thankfully, Python and other programming languages are smart enough to provide the intermittent code, the intermediate code that would convert one of these to match the other. And so when this statement happens, it says, okay, it's adding time. What do I need to know? Well, I need to know the two numbers I'm going to be adding. One of them is an int. The other is a float. Are they the same type? No. Then I need to do something special. I need to convert one to the other format. And so I'm going to make a float as well. And then I'm going to be adding 3.0 to 3.0 and then storing the result. And that's why I got 6.0 as my result. You might have thought that 3 plus 3 is 6. Well, it is. But 3 plus 3.0 is 6.0. The 6.0 means that it's being stored as a float. So if I did this, A is equal to 3, B is equal to 3, and C is equal to A plus B, and then I print out C. Yeah, now it's just a 6. There are places where the program will crash if the wrong format of data is given to it. If it was expecting an integer and you give it a float, it'll crash. And in this particular case, I made the program so that when we ask for our age, we convert it to an int. Now I did that because people usually give their age in whole numbers. But, yeah. So what is your name? My name's F. My age is 3. Okay, next year I might be 4. So my name is F. My age is 32.5. And it blew up because I was trying to convert it into an int. Well, I wasn't, but the programming language was. There's a call right here that says, take my age and convert it into an int. Well, it's not an int because I typed in a .5. It is an invalid integer, and so it crashed. It said invalid literal. If I don't like that, if I don't like the ability for it to crash that easily, I would be better off if I made that a float. And when you're doing this kind of input and then immediately converting it, you can do it in one step rather than 2 if you want. Here's what I could do. I could put the word float there, float parentheses, and end it with another parentheses. And now we are good to go. We don't have to do that data conversion in a separate step. And you'll still see me do that a lot because this could be 3 statements rather than 1, right? Here's what it could look like one way. Print, what is your age? And then age is equal to input, parentheses, quote, greater than, end quote, in parentheses, and then age equals float age, right? Or we could do it this way in one statement. They both work just as well. However you want to write it is up to you. There's only one material difference between the way these work, which is that when it asks for the age, since I separated the print and the input as their own lines, then it goes to the next line before it lets me type in. But when I do it like this, all in one line, it stays on the same line. That's the only difference between doing it that way. So it's up to you. Quite often, I'd rather do it like that. On the other hand, if this was fundamentals of programming and I was going to be making you draw a lot of flowcharts, I might do it like this because if we have 3 things, then listing them separately makes them easier to write a flowchart for it. I'm just going to comment this out because we can do that like that. So the input function builds a string. It's from the user's keystrokes and returns it to the program. So what is a string? It's a series of numbers, ultimately. Even when we type in letters, it's ultimately a series of numbers. If we go to a site that displays the Ascii chart, the Ascii table, this was invented like in 1967. Before then, every computer manufacturer had their own system for encoding text data as the numbers that are stored in the background. And then finally, you know, people wanted to make some agreement so that it didn't matter whether you had a computer by IBM or digital equipment or whatever, then they would all at least be able to read each other's data. So if I had the word Fred in memory, well, an F is encoded as a 70. And then an R is encoded, a lowercase r, as a 114. And an E, a lowercase d, is encoded as a 101. And then a D is encoded as a 100. So when I type in my input, when they ask me my name and I type in Fred, each key press I press on my keyboard generates a different number. I got a 70, and then I got a 114, and then I got a 101, and then a 100. And so if I saved the word Fred out to a file and then open that file up in a specific kind of editor, I would see those numbers. Those numbers would probably actually be displayed in their hexadecimal equivalent. I'm not going to talk about what hexadecimal is. But so a string is just a series of codes that a keyboard generated or could have generated, right? And so it's a representation in memory. And then it's up to the computer and the program to decide what to do with that series of numbers. So when we hit the print and it's trying to print out those numbers, then Python knows, oh, that's text. Okay, well, I'm going to change those numbers back to letters to be displayed on the screen. That's why that step of typing in that conversion to an INT or a float has to be made. Because if I typed in that my age was 33, what the keyboard really sent well, where's the 3? Here it is. Was a 51 followed by another 51, right? And so then if I'm going to say, you know, age equals age plus 1, well, what was our age? It was 51, right? And then so how do we add 1 to 51? Do we get 5152? You know, it's you can't even do math with these sets of control characters, right? They have to be converted into a numeric format. And so we call the int function, or we call the float function, to turn that 5151, which represents 33, into a real number that math can be done with. What if we're curious about the values of what we're typing in? We typed in our name. I want to know those ASCII values. Well, I'm going to write a little loop here that's going to display the ASCII values for those letters. Because otherwise we're going to hit the end of the chapter in 2 minutes, and we don't want to do that. So, although I'm not going to explain the syntax as we go, for letter and name, colon, this sets up a loop where every letter that is stored in the name variable can be processed separately. And we're going to print the letter, and we're going to print the ASCII value of that letter. Python gives us a function that generates that, but they didn't call it ASCII. They called it ORD for ordinal. So print parentheses letter, comma, ORD, open parentheses letter, close parentheses, close parentheses. All right. And so an F is a 70, an R is a 114, and an E is a 101, and a D is a 100. Internally, that's how my text is stored. In each letter representing a byte. Now that's simplifying it a little bit, because what if you have other languages, right? You have Russian, or you have, you know, Persian, Farsi, Korean, you know, North Korean versus South Korean, all those different symbols. They're not just stored one letter per byte, but we'll pretend that's the case right now. We're going to pretend this is the 60s and the 70s, and all we do is text process in English using the ASCII table. So converting strings have to be converted to appropriate number types before we can do the math on them. And so we have the two functions. INT converts a string to an int, and float converts a string to a float. So here's an example of getting input and converting it into an int, all in one statement rather than splitting it up into 3. First is equal to INT parentheses, input parentheses, enter the first number. And then second is equal to INT parentheses, input parentheses, enter the second number. And then print the sum is. So far we've seen just a few functions. We've seen float, which takes whatever's between the parentheses and converts it into a number. Same thing for int. Another function takes a string of digits and converts it into an integer. And then we have the input function. In between the parentheses, you can put a string prompt. The prompt is the message that's displayed on the screen telling them what to type. And it returns a string of characters entered by the number. And all of these things, these results will be stored in another value, right? You don't just type in float 3 because that wouldn't do anything. You say x is equal to float, right? Because you have to store the results into something so that you can use it later. And the same is true for here, right? You know, y is equal to that. You know, or if you get your input, you're going to want to get your input, right? But they're ignoring, you know, the fact that you probably want to just save that data. And then the print function will print the expressions. We can separate each expression by commas. And if we separate each expression by commas, then they're padded out with spaces when we print them out. So if I do this, print 1, 2, 3, it's going to print out 1 space 2 space 3. Print. My name is, comma, Slim Shady. There we go. My name is, and it put a space there, Slim Shady. So we can run Python program files by loading them up into idle or from the command prompt. Now that's if the path is set up correctly to do that. And I'm not going to demonstrate running Python programs from the command prompt right now. So we're just going to right now pretend that the way that you run Python programs is to load idle and then choose file open and then open up your file and then run it, right? When you save your file, you're going to give it the py extension just because the operating system will associate that extension with Python so that it can run it. And then running a script from idle allows you to construct complex programs, test them, and save them in program libraries to reuse or share with others. Width is equal to int input enter width. That's the weirdest syntax. It's like this was not written by somebody who spoke English. Anyways, enter width, right? And then the height is equal to int input enter height. And then the area is equal to width times the height. And then print the area is info comma area comma square units. Yeah, let's do that. Print. Let's calculate the area of a rectangle. W is equal to, now are we going to use I and T like they did? It'll crash if I said that I had a width of 3.5. The decimal point is not an integer, and so it would crash. So I'm going to use float instead. So W is equal to float, input, enter the width in inches. Space, space, greater than, end quote, close parentheses, close parentheses. And we're going to get the height in inches. Same thing, so I'm just going to copy and paste it and put an 8 there. I'm going to say height. And then let's get the area, which is the width times the height. And let's print the results. Print. The area of the rectangle is but I'm going to use a formatted print statement. So I'm going to stick that F there. And then I'm going to print out my variable there. Like that. Okay, the width is 10, the height is 5.3, and okay, looks good. All right, so we have several examples now of getting input and then doing a little bit of math. And one, we just added 1 to the number, and here we multiplied 2 numbers together. I love that this comes here with no explanation of what it is. But anyways, this is the same thing we've been talking about, right? We type in our Python code, and then when we're ready to run it, the syntax checker and translator goes. If there's any errors, it kicks those errors out. It produces, upon successful compilation, stuff that's called byte code. Byte code isn't machine language, but it's something that can be translated pretty easily into machine language. And it's an intermediate level of programming language, somewhere between high level and low level. And the Python virtual machine, meaning the shell and the Python language, then takes that byte code and runs it line by line, taking input from what the user types in. If there are other error messages, it can crash and kick them out, and it will be printing its display on the screen. So, detecting and correcting syntax errors. Programmers inevitably make typographical errors, called syntax errors. The Python interpreter will usually detect these. So what is syntax? Syntax are the rules for forming sentences in a language. Right, in English, we say, you know, the red tractor. Well, that's getting garbled. But in Spanish, the adjective does not precede the noun. It follows it. So it would be El, and I don't know the word for tractor. El tractor rojo. So the syntax of the two different languages, in Spanish, the adjective follows the noun. In English, the adjective precedes the noun. And those are just the rules. Now, you know, humans are smart. And so if I walked up to you and I say, where is the tractor red? You'll probably be able to figure out that I'm looking for the red tractor, right? You'll just think that I don't speak English very well. The computers need to follow their syntax very precisely. So in our language, we do have specific rules, one of which is that every time there's a colon, the next line has to be indented, right? That spaces will separate our keywords. That if you're going to do math, you can do this syntax. Something is equal to something plus something, right? That's syntax. If I left out one of these things, then it's a syntax error. Often there are multiple forms of syntax that will work to solve the same problem. Now that I have that area, or if I just say x is equal to 3 and then I want to add 10 to it, I could say x is equal to x plus 10, or I could say x plus equals 10. Those do the same thing. Just two different syntaxes for accomplishing the same task. Now, in lots of places, the spaces are not necessary. I could remove all of these, right? And the program would work just as well. But, you know, sometimes the spaces are necessary. The spaces are necessary when, if they were missing, the word would actually be different, right? Like if I took this space out, if name. What is an if name? I don't know what an if name is, and neither does a computer, right? 4-letter in name. So to separate the keywords from the values that follow, you know, yeah, the spaces are necessary. But when forming the expressions like this, we just put them in there to make them pretty, to make them easier to read. And so you'll see me usually follow some spacing conventions of putting a space between before and after the equal sign. And some people will say, yeah, you should do that, but you should always take these spaces out. Well, I'm trying to write it to be as easy for y'all to read as possible. And I just think it's easy to read if it's spaced out. Doesn't have to be. So when Python encounters a syntax error in a program, it halts the execution. So for example, length is equal to int input, enter the length, and then print lenth. Well, we left out the G there. There is no G variable, and so it produces an error. It says name length is not defined, and that's true because in G, the G is missing, right? So it's a typo, it's a mistake. So syntax errors are mistakes when we misspell things or when we have typos or we don't follow the rules of the language. The next statement attempts to print the correctly spelled variable, print length. Syntax error, unexpected indent. That's what I mean. This slide here is nonsense because it's not indented. Now it's indented, right? And yeah, if I go to the Python shell and I try to enter a command that's indented, it's going to yell at me about it, right? Unexpected indent. Because the rules of the syntax are that the only time you have spaces, indentation, is when the line above it had a colon. And that's true even in the shell. If I wanted to do this, x is equal to 3, and then if x greater than 0 colon, print, wow, print. You gotta be kidding me, right? And then once I hit enter 2 times in a row, it actually ran the whole statement. But when I did the colon, it started indenting, right? And I had to hit enter to get it to generate a blank line to let it know that I was done so that it could run all that. Now I don't have to do that when I am writing if statements here, right? I did not have to put a blank line here to indicate the end of the if. But I did when I was entering it in the shell, but that's just a quirk of using the shell. We almost never use the shell. Final example, a programmer attempts to add 2 numbers but forgets to include the second one, 3 plus. Well, the syntax is that if you have a plus sign, there better be 2 things. One on one side of the plus sign and one on the other. And furthermore, they better be compatible data types. If they're not, then we're going to get errors. And so that's the syntax error. All right, let's go take the quiz. I'm just going to knock that out of the park. Now, if you take it along with me, unfortunately, your questions are going to be in opposite order. I mean, not opposite order, but in random order. And you may not have the textbook yet. I should make that a homework assignment. Buy the textbook. Anyway, so I'm going to go in and find the unit quiz for chapter 1. All right, which of the following are input devices? a mouse, a microphone, a speaker, or a printer. Now, the funny thing is that nowadays, we have all these smart devices and everything is an input device. Your printer is actually a two-way communication thing, right? Because it's got to communicate, you know, information back to the computer about, the cyan ink is low, that kind of stuff. But anyways, input is for getting stuff in, not sending stuff away. So our mouse is an input statement and our microphone is an input statement, but we're going to say that a speaker and a printer are not. Now, normally I'm not going to do these quizzes for you, but just this one time. Which of the following are general purpose computing devices? Well, I would probably need to go and read the textbook more carefully about what a general purpose computing device is. A general purpose computing device is one that you can load different programs on it and it will do different things. Nowadays, cell phones are general purpose computing devices, but back in the past, all you did is made phone calls on them. So while that's a good answer, these are circles, not squares, meaning that we can only select them. A portable music player, well, it's a computing device, but it's not general purpose, right? You don't load up different programs on it. Well, I don't know, if you buy an iPod Touch or whatever, it's just a cell phone without a, anyways. A laptop computer is a general purpose computing device because you can load your own programs onto it and get it to accomplish any task. It has a way to, type stuff into it and display on the screen, and ways to store programs and the ways to store data on it. Which of the following outputs data in a Python program? Print. Print will output. Which of the following contains information? Oh boy. Ultimately, the entire universe is made of information, right? But we know that a book's got information in it. An audio CD is full of information. A running computer, chock full of information. My grandmother's china cabinet, what if she's got books in it? I don't know. I hate this question. I'm going to leave it alone and hope that I get it right. And we will find out if I get it right or not. What is the set of rules for forming sentences in a language called? Syntax. What is the purpose of the CPU? The CPU doesn't receive input from the human user. That's an input device. It doesn't send output to the human user. That's an output device. It doesn't store information. That's a storage device. A CPU decodes and executes instructions. It just decodes and turns them into numerical operation codes for the chip to process. What is idle used to do? Edit Python programs? Yeah, sure. Save Python programs? Yes, indeed. Run Python programs? Yeah, it sure does. It does all of the above. Which of the following are examples of algorithms? A set of instructions for building a shed. Yeah, it's a set of instructions for accomplishing a task. A recipe. Definitely an algorithm. A spell checker. No, that's a program. It's an implementation of an algorithm, but it's not an algorithm. Just like the shed you build is not the instructions. Those are two different things. And then a dictionary. No, that's a collection of information, but it's not a series of instructions. Which of the following are output devices? Now, again, a scanner is an input and an output device, but they're not going to want me to say that it's an output device. A keyboard is not an output. A digital camera is not an output. A monitor, yes, that is our output device. Which of the following translates and executes instructions in a programming language? The text editor just saves the text. The compiler translates the instructions but does not run them. A loader would just load something into memory. So the interpreter is something that does both the translations that a compiler can do and execute these statements right on the spot, which is how Python does it. So the interpreter translates and executes instructions. And I missed one, so let's go and review the test. Looks like I got that one correct about the mouse and the microphone. The laptop is the general purpose computing device. I guess I could skip straight to it. Oh, well, what do you know? It wanted me to say that a spell checker is an algorithm. I strongly disagree. A spell checker, just like a recipe is not a cake, a spell checker is an implementation of an algorithm. But okay, so when you take this quiz question right here, please remember that they think that a spell checker is an algorithm. And since that's what they think, you're going to check that so that you get the 100. So I should just retake it again, giving all the same answers. The questions are in a different order, but it's the same questions. And then I would just make sure that I did that as well. All righty. So are we going to continue or are we going to call this close? I think we need to continue, but I need to take a break. So I'm going to pause the recording and hopefully remember to restart it. So what's our homework for chapter 1? Well, homework is just to get the textbook, purchase the access to Cengage, log on, take the quiz that I just did, and then to prove that you have it, take the screenshot of your score in the chapter 1 mind tap quiz, and then upload the screenshot here. All right, so moving onward, we're going to hit chapter 2 now. But while I have mind tap open, watch the following animations. Help explain.
What is a computer program? In this segment, we're...
Well, that's interesting. So unlike what I did, you're actually going to want to read the text, right? I'm just not going to go through every page of the text during the lectures. Where's the search function? If I wanted to find out what a general purpose device is. General purpose. In what sense is a laptop computer a general purpose problem-solving machine? Well, good question. It didn't take me to the definition of that, but you'll find it if you keep looking for it. All right, we'll grab chapter 2. Should be a way to hide the toolbar up here. Oh, okay, there we go. All right. So, software development. The process of planning and organizing a program. Several approaches, one of which is the waterfall model. The waterfall model of programming is this. You get a request from a customer. And you verify the request. Yeah, they're a good customer. It's worth thinking about. So we analyze the problem. After we verify our analysis, we may have to go back and talk to the customer and find out if it meets the request. If not, then we keep verifying it. And then once our analysis is done, when we can begin the design. And if it is got to verify our design, and if it's good, great. If not, we need to go back and check our analysis and maybe do some more analysis. Anyways, you can see why it's called a waterfall. It's kind of, you know, stepping down, stepping down, stepping down. And any one of these steps, unfortunately, you might have to get kicked all the way back up to here to fix it, right? If we've done integration testing and it turns out that they wanted it to be able to, you know, display text in both lowercase and uppercase, but for some reason you made it only uppercase, you might have to go all the way back up to the beginning and, you know, validate with the customer, you said uppercase only. And they said, no, but we really wanted lowercase. And so then a whole trickle down of all the results, consequences of that. Anyways, a waterfall model. You analyze, you design, you do your implementation, you do your test and your integration, and then finally is the maintenance. What is the maintenance? Well, you know, the program's great the day that you implement it, but it turns out that somebody wants changes to it later, or somebody finds bugs in it that you know, that they didn't spot before it was running, or what was valid at one time, it turns out that the sales taxes have increased and you did not put a way in for them to modify that, so you got to make a change to the program to let them put in new sales tax. That kind of stuff. That's called maintenance programming. And you're familiar with that idea because nowadays, you know, games come out and the publishers, you know, basically dump them on users in an unfinished state, and then they hurriedly go and try to fix as many problems as possible. They keep pushing updates out. That's the maintenance programming. Programs rarely will work as hoped the first time they are run. The cost of developing software is not spread equally over the phases. Usually people just spend a little bit of time doing analysis. They do more time during design. They do more time doing implementation, and then more time doing integration, more time doing maintenance. Well, this isn't really the amount of time, but it's the cost of correcting a fault. If you fix a fault in the analysis stage, it's a lot better than waiting until after it's been published and it's on 1 million users' desktops, right? Then the cost of correcting that fault is far greater. So text processing, this says, is by far the most common application of computing. Email is a form of text processing, so is text messaging. Web pages, believe it or not, are just text. If we go and we view a web page and we right click and we do view page source, we'll see a bunch of text, right? all rely on and manipulate data consisting of strings and characters. So data. Data type consists of a set of variables, a set of values and a set of operations that can be performed on those values. So for example, an int. An integer is a data type, so that defines the kind of values that can be stored in it. And the fact that it is a data type also specifies what can be done with those numbers. You can add numbers, you can subtract them, multiply and divide them, and take them to the power of, things like that. Maybe I'll start a new file called Lecture B2. So if we create a variable, that is an int. The data type is int. The data type specifies its format, which is a series of bits that represents the numerical data, and the operations that can be done on it. So the data type specifies what the variable can hold and what can be done with it. So what can be done with an int? Well, you can raise it to the power of something, right? We could say a is equal to a to the power of 2. That'll square, or 3, cube it. Now we're going to create another variable. That's a string. If we tried to do the same thing to it, you can't take a word and raise it to the power of 3. So that is going to be a syntax error. Yep. Unsupported operand type. What if we did this? A is equal to, how about if we do print A times 10? So we're going to cube our number and then we're going to multiply it by 10 and print the results, which is 270. Now this one's still crashing, so I'm going to get rid of that one. But what if we did this? Print B times 10. Well, that's a number. I mean, that's not a number, that's a word. How can we multiply by 10? Well, it's kind of interesting what it does. 333, 333, etc. Right? So it just repeated it as many times as we specified. And do we find that real useful? I don't know. Not normally, but if I ever wanted to print exactly 80 asterisks, I know how to do it. Print an asterisk times 80. And then boom, right? So the operations you can do on a string are different than the operations that you can do on an int. However, the asterisk works on both of them. They do slightly different things, right? This one does math and this one does repetition of a string. Same for plus, right? I can use the plus sign on strings, but it does concatenation, right? Print B plus fun, right? I'm using the plus sign, but it doesn't mean math. It means concatenation. Take this string and append it to that string so that it can be printed out. So an int supports all the arithmetic operators. Which are addition, subtraction, multiplication, division, something called floor division, and then modulus, which is a percent sign, and then star star, which means to the power of. So star star is to the power of. Slash slash means floor division, which divides and rounds down. And percent sign means modulus, which I'm not going to explain at this point. It just means remainder. So if I come up here and I do A is equal to 3, and then I do B equals A divided by 2, or heck, let's just type in A divided by 2. Well, that's 1.5. But if I do A slash slash 2, that means floor division. That means divide and round down. And 3 divided by 2 rounded down is 1. So strings support addition, which is concatenation, appending, and star for repeating. That's really the only two math symbols it supports. You can't use a minus sign. You can't use to the power of. So ints and floats are numeric data types. They represent numbers. Numbers that are ints are whole numbers. They have no fractional component. They can be positive and negative, of course. Real numbers are numbers that do have fractional components. So those are the floating point numbers. They have a decimal point. And then character strings. Character strings are just anything between quotes. So in Python, a string literal just meaning value, is a sequence of characters enclosed in a single or double quotation mark. So if you have single quote, or you have double quote, that's the empty string. So you get to pick. And some languages are very picky about how, when you use single quotes and when you use double quotes, but Python is not. So if we wanted to say, my name is Mud, well, that's not going to work, right? Because I used a double quote here, and so it thinks that that's the end of the string. So I'm going to mix things up by making these apostrophes instead. Or I could have done it the other way, right? I could have opened up my string as being made with an apostrophe at the beginning and the end, and then I could have put double quotes here instead, right? It's totally your choice as to whether you use single or double quotes and when you use them, right? You use triple quotes for long multi-line paragraphs. Now, normally I say that I'm making a comment when I do that, but it is actually a string. So data is equal to quote, 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 my name is Mud, quote, 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 right? And then I'm going to print my data out. And it did. It printed out my name is Mud. So you can use these triple quotes to make long multi-line comments, which is what I most commonly use them for, but you can also use them as a data storage in order to assign multiple lines of text into a single variable. So if we did this, print, I want to And I'm going to put a \n here. Go to sleep. This is called an escape sequence. Escape, the backslash starts the escape sequence. And escape means just stop doing your normal processing and switch modes to something else. And the mode that it's switching to is to decide what to do, dictated by the character that follows the backslash. And \n means new line. So it's going to print out, I want to, and then on the next line, it's going to print, go to sleep. So that is an escape sequence. There are others. There's tab. Print 1 \t, 2 \t, 3 o'clock rock. So it's going to print out ones, couple spaces, 2 couple spaces, 3 o'clock rock. So \t is a tab, \n is a new line. There are others still. There is a character that represents a single quote, an apostrophe, and another one that represents a double quote. So print, my name is, now remember when we did it like this, previously it didn't work. I had to go in and I had to change these to single quotes or these to single quotes to get it to work. But I could have also done it with escape sequences. If I put a \quote, that will output a double quote. And so now it's going to print my name is Mud, and it's going to have quotes around it. It's going to look nice and pretty. It's not going to be using this feature of mixing single quotes and double quotes in order to accomplish its task. Instead, it's using that escape sequence there. So, and as promised, my name is Mud. Or you can do the same thing with apostrophes. What if you need to use a \? Now, Microsoft and Bill Gates were silly when they chose \ as the character that separates lines in a file, right? Everybody else, every other operating system uses /. And these \ are kind of annoying because what if I wanted to put a path in my file that looked like this? File name is equal to C:\temp \names.txt. And let's print that file name. Looks good, huh? Well, it's not going to look good. C:, that \ is being treated as a tab. And then this \n is being treated as a line feed. So it's going to the next line. So that just looks absolutely terrible. Two ways to fix it. One is that we could join the rest of the universe and use /. And // do actually work on Windows. They just, due to what IBM and Bill Gates decided in 1980, the operating system displays them as \. But this will look okay. It won't be garbled now. It looks like a Unix path or, you know, a Linux path or a Mac path rather than a Windows path, but it works just as well even on Windows. Or I can use double \. And the \ means, okay, this is an escape sequence. Now tell me what you want to do. And then the second one says, oh, okay, you just really wanted me to print a \ out. That's what you really meant. And so now it's going to look okay. But I would just get used to always using /s for my file names. If I was going to embed a directory path in my program, I would just use / rather than using \ like that, because the double \ looks weird. It prints out fine, but in the code it looks weird. So we've seen several different escape sequences as of this point. We have seen backslash, no wait, backspace. Backspace is a weird idea, right? Print. My name is Mud. Backslash B, backslash B, backslash B, Fred. And backslash didn't work, so I don't understand the point of them listing it as a escape sequence because it didn't work. In some environments, it actually would have backspaced over it, and we would not have seen Mud there at all. It would just say Fred. But that was a failed effort. Slash slash gets translated into a backslash. Slash T is a tab. Slash single quote is an apostrophe. Slash double quote is a double quote. The only one you really use often is new line, and then to a lesser extent, a horizontal tab, a slash T. So string concatenation is when you use a plus sign to append pieces of text together, right? Hi plus there plus Ken. Hi there, Ken. Or you can use the asterisk to repeat a string. Print 10 spaces followed by the word Python, right? There's a space between those quotes. So we're saying space times 10 plus Python. And so it puts 10 spaces in a row there and then prints out Python. And I demonstrated that to you with asterisk or whatever. It's the same idea. So like print, come on. Ten times a dash, quote, dash, end quote. It's going to print 10 dashes. So a variable associates a name with a value. There are more technical ways of putting it than that. A variable has a named location in memory that can contain a value, which makes it easy to remember that number and use it later in a program. And so there are rules about naming variables. It cannot be one of the reserved words of the language. It can't be an if or a def or an import, because those are all keywords for the language. The name must begin with a letter or an underscore. It can contain any number of letters, digits, or underscores. After that, they are case sensitive, so that weight is different from weight. And here's a tip that I don't often follow when I'm teaching, which is to begin each word in the variable name with an uppercase letter except the first one, interest rate. That's great, and I agree with it. And if I'm doing professional programming and getting paid for it, I probably would do it that way. But if I was typing it in for students, I would probably type in interest underscore rate. Because once I start typing in uppercase and lowercase letters, that just means that half the people are going to get the uppercase letters wrong, right? They're not going to uppercase them, or they're going to uppercase them sometimes and not other places. And so it becomes a mess. So I tend to, just in my examples, use all lowercase letters separated by underscores. But this is considered the modern way of doing it, and has been for like 20 or 30 years. Instead of using underscores, you capitalize each letter. So, you know, your birth date, like that, right? First name with a capital N, that kind of thing. You know, mass in grams, that sort of thing. Now, by convention, if you create a variable that's all uppercase, it's supposed to be considered a symbolic constant, a value that the program never changes. Now, Python does not enforce that. Some languages do enforce that if you make something a constant, if you try to change its value later, it will generate an error. Python doesn't. But if in a program you see a variable name that's in uppercase, what it's telling you is that once it has been defined, its value should not change. So examples, tax rate or standard deduction. Let's go look at in the modules. There should be downloadable files. Let's see downloadable data file for chapter 2, unit 2. It's a zip file. Here we go. It's a program, tax form. Compute a person's income tax. And he's had a lot of comments. There's a value for tax rate, for standard deduction, and deduction per dependent. The input that it asks for are gross income and number of dependents. And then there are some computations, and the output is the income tax. So here are the constants. Our tax rate is 20%. Our standard deduction is $10,000. Each dependent we have is worth $3,000. So we request the input. Gross income is equal to float, parentheses, input, parentheses, enter the gross income, the number of dependents. Since you don't have a partial number of dependents, you don't have 2.5 dependents, he feels safe in just asking it as an int rather than a float. So number of dependents is equal to that, and then compute the income tax. The taxable income is equal to the gross income minus the standard deduction minus the dependent deduction times the number of dependents. And then the income tax is equal to the taxable income times that tax rate, and then that's how we do that. So these are constants because our program is not supposed to change halfway through the tax rate. We're not supposed to decide, 3/4 of the way through that, oh, by the way, the standard deduction got to change, or suddenly we get to now deduct more per dependent than we did before. So variables serve two purposes. They help the programmer keep track of data that changes over time, and they allow the programmer to refer to a complex piece of information with a single name, which is called abstraction. So here's a program, and at the top of it, he's added what's known as a doc string, which is when you begin a multi-line comment with triple quotes. Now, when I did my comment, I did it as marks like that, but I should get in the habit of doing it the way that they showed it in the book. I'm not sure why I'm saying I should, but I think I may switch over to that this semester. So lecture B2 would look like this. It's June 3, isn't it? Yeah, all right. And so on. Okay. Honestly, I liked it better the other way. But what we're supposed to do is we're supposed to describe who the author is, the last date that it was modified, and then the purpose of the program. So let's write a program that'll ask for a number and then calculate the area of a circle. So we'll do that. So here's how my program might have started off looking like, right? Except it's not written by him, it's written by me. purpose of the program is to compute the area of a circle. The input is an integer, the floating point number representing. The output is a floating point number labeled as the area of the circle. Okay, that's way more description than I would normally put in a program. Normally I would say this program calculates and displays the area of a circle based on its radius. Well, let's do that though. Let's get the area of the circle. Radius is equal to the float. I'm using float because I want them to be able to type in decimal points, parentheses, input parentheses. What is the radius of the circle in inches? Space greater than, end quote, in parentheses, in parentheses. Why so many parentheses? Because I had 2 opening parentheses. I better have a closing parentheses at the end. One for each of those. I'm going to take out the part that says is in inches just to make it shorter. All right. So we've got our input. Now let's calculate the area, which is just pi r squared. Well, how do we get pi? We can have Python tell us what pi is, but right now I'm just going to cheat and use a constant. So I'm going to define a constant. Pi is equal to 3.14159. And I'm going to say area is equal to pi times the radius star 2, which is pi r squared. And then we can display the results. Print the area of the circle is end quote, comma, area, like that. All right. I'm going to change the name of this from Circle PY to Lecture B2. Leave that alone. All right. So I think we've gone about far enough, but we do need to have some homework based on this idea. So write a program that will ask the user for a number of yards and calculate and display the number of inches. The formula is inches equals yards times 3 times 12. Because there's 3 foot to a yard, there's 12 feet to 12 inches to a foot. Okay, that's part 1. So we're going to make it do several things. So let's rewrite this to say to write a program that will perform the following tasks. Ask the user for the number of yards and calculate it as inches, right? Ask the user for a number of feet and calculate and display the number of miles. And 5,280 feet per mile. And ask the user for a radius of a sphere and calculate and display the volume of the sphere. The formula for that is, I better look it up. Four-thirds pi r cubed. That should be enough. That'll show that you've got idle installed and that you have the basic idea of getting user input and doing math on it and displaying output. All righty, does that make sense?
Yes, it does.
All righty. So I'm going to go ahead and stop the lecture here, and there should be a Dropbox for uploading comments about the lecture. Make sure that that's true. I'll wander off. Yes, there is. All right, so there's a lecture B. Okay. All righty. So do you have any questions?
No, I don't. Outside of the mutual technical difficulties, you're doing a great job explaining things. So
Oh, well, thank you.
I'm enjoying the lectures.